We have 3 non-rationals. Perfect. Okay, so let us then start with a sort of a reminder what we are doing. Oops, wait a minute. So what is our goal? We are somewhere in the beginning of developing the stochastic calculus. So what's that? The overall goal is sort of a dream, okay, very local dream, of course, is to have a large class of processes to define something like this. The integral of some process against another. Plus, of course, some rules, some calculus for such integrals. And the analogy you should have in mind is just differentiable functions, so you can always integrate one differentiable function with respect to another. So this is just the primitive of xy prime, and the calculus is basically just integration by parts. Okay. Ideally, what we also would like to have is that this class of processes, or maybe a slightly smaller class, is closed under such operations. Again, like differentiable functions, and also is closed under some other operations like compositions maybe, or taking whatever nice functions of x, nice functions of several processes. I mean, you know, to have really some working machinery. So last time it was the very simple first step. So the second reminder is that if y is a finite variation process, and for finite variation processes, I always assume that they have continuous trajectories and plus y. They vanish at 0. Okay, so for me, it's going to be just the part of the notion of finite variation process. And x is whatever you wish, such that okay. This is finite, and x is progressive. And progressive means it's measurable with respect to ft tensor b0t. Then, okay, we can define this, and well, this is again a finite variation process, and it is adapted. So here what you do is, perfectly deterministic thing. So you just define the Stieltjes integral, and that's it. The only small tiny issue is to check that this is adapted. Okay, some formalities about measurability. Okay, good. So today we are going to do something more interesting. Well, at least not that boring. And to start with, let me discuss Still not the construction we really need, but some particular case which I hope is rather instructive. So what what is the other somehow trivial situation when there is a reasonable notion of the integral? So let this be, and from now onwards, I will assume that everything is defined on the half line. If we have a smaller segment, just think otherwise. Consider something like this. So if you have a process which is defined only up to time t, just stop it there and think it is a constant function afterwards. Okay. So assume that t is infinity. Well, it might happen that you are working on an open segment, but modifications are more or less trivial. So for simplicity, t capital is infinity. So let it be deterministic bounded variation function. And again, I assume that it is continuous. And say 0 and 0. And Bt be standard Brownian motion. So what could be the natural definition for such an object? Okay, this is not a bounded variation function. Well, formally we didn't check it, but it's not. And so you cannot use Stochastic integration, but instead you can just say, okay, I know how to do it other way around. So let me proceed this way. Okay. Well, some definition. And I'm going to use the notation. I already introduced it. Instead of writing all this, I mean the integral 0t, blah, 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 I will also use this notation. Okay. Anyway, we're defining some objects, and why should we write this complicated expression? Well, okay, then the question is if there are any reasonable properties, I mean, how to play with this. Because, of course, at this moment, nothing happened. I just said, okay, if I have a bounded variation function and the Brownian motion, then I would like the standard integration by parts to be true. Okay? So let us make some observations. So assume A is just, okay, no, not this way. Okay, just not assuming anything, just note that this integral can be thought about as a limit of finite sums, right? So let me write it this way. This is the limit over the set of partitions of the segment 0t. Okay, so I'm always, this is the notation I'm going to use continuously, so I'm always working with the partitions of the interval, which I denote this way, and I often drop the superindex n. Okay, formally it should be also n here, And I always assume that at least the mesh size tends to 0, and often I also assume that partitions are nested in a sense. Each next is a subdivision of the previous one. Here it's not important. It's just a definition of the Stochastic integration, right? There is some issue. I put here Tj. This is for some purpose, and we will see this in a minute. But for the definition of the integral, it's actually of no importance, right? So for the Stochastic integration, I can take here any point on the interval Tj minus 1 Tj. Okay, and then I can rewrite, this definition. So what I see is that, there's just trivial identity. This is the limit of the sum a Tj minus 1 Tj minus b. Okay? That's exactly this is the identity which exactly leads to the integration by parts for the Stochastic integral. Okay? And here now, here I had Tj, and here this Tj minus 1. Well, what's nice in having here Tj minus 1, just a remark. So then let us compute the expectation of ABT squared. Well, hoping everything converges. When I square this sum, what happens? There are some cross terms, right? But the cross terms, they're basically the increment of the Brownian motion on one of the segments by the increment on the other segments, and they're independent, so the expectation is 0. So, okay. Assume, for instance, that A is a bounded, it's a deterministic bounded variation function, so it's bounded on the interval. Then it's a totally legal computation, so first I have this, and should be expectation somewhere, namely here, right? And then I'm just saying, this is Tj minus 1, right? So what I have is just the integral of a squared. Easy. The only important thing is that here we had j minus 1. Okay, I made a clever choice on the previous line. Okay. For deterministic functions, it doesn't matter still. If A is deterministic, then it works. Okay. Later on, it's going to be non-deterministic. Okay, good. But now what I can say? I can say, all right, I have a sort of an isometry in L2. So my original construction gave me the answer for nice A. I'm constructing such an object. And I have a recipe how to construct it for nice A, which is bounded variation, or maybe even differentiable. But now I can just complete it by isometry, right? So what I have a definition of this ABT for A in L2, say local 0 infinity. And by local, I mean L2 on any finite interval. Just using the isometry of Hilbert spaces.
Do you use something like the fact that bounded variation function is everywhere dense?
Yeah. Somehow implicitly, well, not even implicitly, yeah. This is exactly the fact I used at bounded variation functions. Even differentiable functions are everywhere dense. Moreover, what we will do, if later on we will use as the basic set of functions the step functions, but Okay, here it's bounded variation. Still, this is a proper definition. Okay? Good. So this is called the Wiener integral. I mean, this integral for deterministic A's is called Wiener integral. So it is called deterministic A's, the Wiener integral. And in fact, it is very much related to the discussion we had when I introduced the Brownian motion. You remember this formal distribution in some space of generalized functions, I mean this formal law. Then you can just think about scalar products, about averaging of the scalar product against this distribution. Okay, but what's important is that in fact it works well not only for deterministic functions. Now let AT be still a nice process, bounded variation process, which also has some randomness inside. Okay? So is an adapted finite variation process. What we actually used in this computation, let us rethink about this computation. So when I have a cross term, I have ATJ minus 1, ATK minus 1, but still I have the increment of the Brownian motion, which is right afterwards, okay? Which is independent of everything else. And ATK minus 1 is measurable with respect to FTK minus 1, because this is an adapted process. What I mean is that actually this computation still works, right? Moreover, here it still works because formally what I have is an expectation in front, right? But I can move it to there. I mean, just saying that, okay, this is independent of the sigma algebra, so I still have Tj minus Tj minus 1. Good? The message is that we still have this identity. So now it's going to be another expectation in front, so this is just the still the random object on the right. Okay? Is it clear what happened? I mean, this is exactly the same computation. Is it clear? I mean that everything works provided I put here Tj minus 1. And right now this is important. It was not important before, but now it is important. And so I again have a chance to just to complete this by isometry. Okay? So if I say no, that this expectation is finite, which basically means that my A is square integrable, then okay, I have a reasonable recipe to define what is AB sub t, at least for a given t. Okay, this is just a sort of an intuition. I'm not going to make it really formal, just because what we need is a more general version of the same idea. But this is a sort of an instructive example. Okay? Good. Now yet another instructive computation. And as I mentioned, the whole idea of these small paragraphs is to give a set of instructive examples of what we should expect. Okay, and the third computation is quadratic variation of the Brownian motion. Okay, just basically a single proposition. Let us start with the standard Brownian motion. And some deterministic sequence of partition of the interval 0t. It's important that it's chosen independently of the Brownian motion. And let be deterministic sequence of partitions. Zero t with a mesh tends to 0. Then there are two simple facts. First, if I compute the quadratic variation of the Brownian motion, let be J, what's that? Just a sum of squares, not a sum of absolute values. Okay, and take a limit as n tends to infinity. This is a random variable, right? So it has a randomness inherited from the Brownian motion. What I have is just t, but I must specify in which sense, right? I'm saying that the random variable has a limit t in L2 in particular in probability. Okay, so I have a convergence. What it says that if I subtract t and square, then the expectation tends to 0. Okay, this is the convergence in L2. Convergence and probability, just a basic reminder, is that the probability of any event that the difference is greater than 1 over 100 tends to 0 for any choice of 100. Okay, and B, if I think about the construction I already had on the blackboard, which is now hidden, I can maybe try to show it here. Yeah, right here. And take the limit of the sums for the Brownian motion. What I have is 1/2 bt squared, quite expected because it's going to be integral b db, right? It should be b squared over 2, but minus t. Again, this is just a very simple and quite straightforward computation, so let us prove it. First, it's easy to note that A and B are actually equivalent. Why? And again, the convergence is in L2. Why A and B are equivalent? Just because it is a simple identity. If I subtract one from another, then hopefully I just have b squared. At least this is how it should work. Right, if I just sum these guys, what's in parentheses, this is btj squared, okay, plus, if plus it's better, right? This is btj squared minus btj minus 1 squared from here. So everything cancels out, and what I have is bt squared. It's just an identity. Because of that, these two statements are, you know, very equivalent. Okay, they are just equivalent. And now let us prove A. And to prove A, again, nothing hard, just compute what is the expectation. And by independence, okay, even without any independence, so this is just the sum of expectations, and each of them is Tj minus 1. So this is sum of Tj minus Tj minus 1. This is okay, so the expectations are T, and the variance and here I need the independence, so the variance is sum of variances. Now I should know what is the variance of a normal variable. Any guess? What is the variance of the normal variable with of the standard normal? 0, 1. I already asked it, you know, in one of the first lectures. The answer is 3. Okay, you either compute it, or you remember some Hermite polynomials, or if you need a more sophisticated argument, there is what's called Wick rule for Gaussian distributions. So the expectations of a product of 4 should be the sum over all pairings of the expectations of AB by CD, expectation AB by expectation CD, expectation AC by expectation BD, etc. There are 3 terms, so you have 3 T squared. And minus 1 because, because we are computing variation. So here it was a digression. So here just a straightforward computation. You have 2 Tj minus Tj squared. It's nothing but the variance. This guy. I know, well, okay, it's clear that it tends to 0. Just because it's less than T multiplied by the maximum of all the increments, which tends to 0. Okay?
Do you can mean L2?
Pardon? This is exactly what convergence in L2 means, because what I actually have proven is that, what's that? This is exactly the expectation of this random variable minus T squared. This is exactly what this means. Okay. Good. Now, some remarks. So, the first remark is about the variation. So, as we see that the quadratic variation is something meaningful, of course, we should, I mean, it immediately follows that the variation, I mean, the limit of the sums is plus infinity, almost surely. Why? Just because, well, it's obvious. It should be a way to write some obvious estimate like maximum like the quadratic variation over the maximum. Okay. this tends to t, and this vanishes. The second comment is about the definition of the quadratic variation itself. So one can choose, and you might try this as a more natural idea, to define the quadratic variation in a pathwise sense. What it means that, okay, given a trajectory, given a sample of the Brownian motion, just consider the supremum over all partitions of the same sum. Over all partitions of this segment. The claim is that it does not work, so be careful. This is plus infinity almost surely. I'm not going to discuss it in any details. Let us leave as an exercise, but this is not, a big surprise, right? Because if it was a function of finite, if a given trajectory was a function of finite quadratic variation, then what you would expect is that this is Hölder 1/2. And Brownian motion is not Hölder 1/2. So the difference is that here we adapt the partition to a given sample. And what's happening here is that we fix it from the very beginning, right? That we do not allow ourselves to tune these points to special points of the Brownian motion. Remember all this discussion that the trajectory has some special and typical points. And basically here the supremum is obtained when you adapt this partition to these special points. And this is not well to know. Question? Okay. And the last comment is, I already said it in words. It seems that, okay, this is not very mathematical, but it seems that if we play with such definitions, then that the natural definition of this object, integral b db, is not b squared over 2, as it should be for nice functions, say for bounded variation functions, but with additional correction by t. Right, because, okay, here, if you just start with this computation, then you can say, okay, it is not very natural because why at all did I put here tj minus 1? Right. Maybe it was more logical to consider a half sum, a mean of btj minus 1 and btj, and then what's going on is just b squared, of course, right? But the actual motivation for taking the value on the left end of the segment is here, right? Because we would like to complete this by some isometry. And for this, okay, here is a natural way. Okay, any questions so far? Well, if no, let us start doing all this in a more systematic way. So what's the current goal? From what I already said, it is not, that hard to extract a definition of the integral with respect to the Brownian motion, of some reasonable process with respect to the Brownian motion, and even some algebra with such integrals, like, to, well, any sort of such identities. But our goal is, in fact, more general. What I would like to do is to define this object integral x dy, not only when y is a Brownian motion, but when it's again maybe this process, or maybe even some more complicated. I mean, so what I would like is, really have a rule how to proceed when y is general and x is general. Okay. So the next paragraph. Quadratic variation of a local martingale. Okay, some terminology. And here we are going to prove, a rather serious theorem, which is in the heart of the whole subject. But first, some terminology of what local martingales are. Maybe it was already introduced by How? Nope. Okay, bad luck. Okay, terminology. This is called a local martingale if there exists a sequence of stopping times, let it be increasing sequence of stopping times, this is for convenience. I mean, it doesn't change anything stopping times, such that for any n, if I just stop at time tn, what I have is a martingale. And they tend to infinity almost surely. If you never saw it, looks a bit strange. I mean, what's the difference? And let us just consider an instructive example. Imagine I do the following. So I just take standard Brownian motion. And then I stop it when it hits -1. So let sigma be the infimum of all s, such that the s is -1. It happens with probability 1. Then what I'm going to do, I would like to continue afterwards. And because of that, I just map everything onto the... Okay, let me just write the definition. So what is MT? MT is B T1 minus T okay. Like this. Nope. Nope. Yeah, I cannot write it in a proper way. Sorry, it was correct. Yes. So what I do here is the whole trajectory of my Brownian motion squeezed onto 0, 1 instead of 0, infinity. And at some point, it hits the level -1, and then I stop. And this is basically -1 for forever. This is my trajectory. Is clear what happened? What I'm saying is that this is not a martingale. And the reason is it has continuous trajectories, by the way. So because Brownian motion hits this level -1 almost surely. So, but what I'm saying is that it's not a martingale. Why? Okay. It is not a martingale. Just because the expectation at time 1, it's m, is -1. Okay, that's strange for martingales. So it is a martingale on 0, 1 excluding 1, but then, oops, something bad happens. Nevertheless, it is a local martingale, so a sequence of these times, where is the example? Would be here. So these times are called either localizing or reducing. I don't know what is a more common terminology. So well, you can think about, say, either well, the first moment when it hits it hits the level n, or if it doesn't happen, or n. So you stop when either you hit here some large level, or if it didn't happen and you first hit -1, then okay, you continue until some big time. The message is that if you stop at this moment, then, okay, trajectory is something like, one of the possible samples would be here. You just continue on the red, and this is a martingale. So here is an instructive example. What is the idea of considering such a more general class of processes? Well, just because you would like to have your calculus not only, say, for bounded functions. So if you assume that everything is bounded, then of course the notions are equivalent. But as usual with calculus, so you may assume that there are some singularities which appear or something of this sort, and because of that you would like to have a slightly more general notion. Okay? What is the important message? The important message is that Dub's maximal inequality is not true for local martingales. So this is a very important tool, and it just does not work. Like here, so it's a good example because many things can be computed explicitly. So like here, the expectation is 1, but if you take the expectation of the maximum squared, it's infinity, I think, or at least the maximum in sufficiently high power. Well, yeah. So here is an example, and then, yeah. Well, I mean that there are, given n, there are two scenarios. First, it reaches this level, or it does not. If it reaches, we just stop, and this is something small. If it does not, then this infimum is infinity, and this is n. Okay? So for any given trajectory, there is enough high level such that they're just n after this level. Yeah, this is a good question, but I think it works. Well, yeah, what else I should say? So 2 remarks. Well, maybe more. 3 remarks. This I already said. Doomb's maximal inequality fails for local martingales. Even with continuous trajectories, I mean, even if you assume that they are in LP, okay, it doesn't help. B, okay, this is a part of this warning. If you assume that the expectation is finite, maybe does the absolute value or square or something like that, again, is not enough to guarantee that a local martingale is a martingale. Is it true? Okay, for p less than infinity. And the positive remark is, okay, but what do we need to say that a local martingale is a martingale? Obviously, what you need is a sort of a dominated you need to have a right to apply a dominated convergence theorem. Because you know something about conditional expectations of m t minimum tau m, and you would like to pass to the limit. So if there exists z positive, this is a random variable, random, such that almost surely mt less than z for any t, say on a finite interval, and it is in L1, then this is a local martingale. A local martingale is a true martingale. This is a simple exercise to check dominated convergence. Okay. Let us make a break and then continue. Okay, so let's continue. It's okay. Just a small remark. Another example of a local martingale, which, as far as I understand, is not a martingale. It's a shame I don't know this by heart. Another example. Just to give you an idea why it's not an unnatural notion which is needed only for some, crazy formalists of mathematics. Another example is 1 over bt. How should I denote it? I mean, where this is the standard 3-dimensional Brownian motion. We definitely would like to have a machinery which allows us to do computations with such objects, right? I mean, so that's what I meant, that it might happen that there are some singularities that your Brownian motion might visit or something of this sort. Okay. Now the theorem. different script because it's important. I mean, this is really the important theorem here. Let us assume that we have a local martingale with continuous trajectories. Again, the same remark. So if it was a martingale with almost surely continuous trajectories, then I'd redefine it on a negligible set by whatever, by identity 0. And I always assume that my filtration is complete, so I do not lose any measurability. Okay, with continuous trajectories, and that's it. Right? Nope. Before the theorem, I needed another proposition. Okay. Then there exists unique increasing process which I'm going to define this way. So this is still a random process, such that, and again with continuous trajectories, meaning without jumps, such that this is a local martingale. So what's going on? Imagine you have a Brownian motion. Then you know what this process is. This is just a deterministic function t. Yes, just t. What I'm telling you is that it happens for any local martingale, which is not a completely trivial statement. I mean, even not that you immediately guess. So, and moreover, it can be constructed exactly in the same manner, so this is a quadratic variation. Moreover, for any sequence of nested subdivisions. Well, actually, nested is not necessary, but what I will prove is nested. 0, t with mesh smaller and smaller. You can construct this as they commute, so is it clear why this is the case? So what I'm doing, I just write, okay, here it was an expectation of the sum squared. Right? And then I open all the brackets. Then again, all the cross terms cancel out because of the Martingale equality. And then I say, okay, how should I do it? I should just say, oh, yeah, of course. I should just say, okay, this is less than maximum of this multiplied by n because of my choice of stopping times. Because I stopped my martingale when this supremum was n, right? So this is definitely less than n for each of the realizations, for each of the statements. And then I say, aha, now I know that the vector is a continuous, so this comes to 0 as Cartesian reference. So what I see is that this is 0, so what I know is that NC is a 0. And then I know, since there's this times, there's localized times converge to infinity, I also know that NC is the limit b equal m tends to infinity m. Okay, so kind of basically the only argument is here is that I can, when I think about the expectation of the square of a martingale, I can always split, or the increment squared, I can always split this interval into many, many smaller and derive the sum of smaller increments squared, which is guaranteed by the okay, so model of this proposition, so what we also know is the immediate corollary. We know the uniqueness part. Just imagine you have two such processes, then you subtract this from another this, this from that. So what you see is that the difference of the first candidate and the second one is a local martingale, is the difference of two local martingales, and a bounded variation process, a finite variation process, is the difference of two increasing processes. Okay. Well, I didn't tell you why a difference of two local martingales is a local martingale. This is an exercise. Think about it sometimes. And so we know uniqueness part. Okay. Well, okay. there are two ways, either to say this is an exercise or to make it on the blackboard. I find it important. Basically, everything the rest in the theorem is more or less formalities. It's okay, not completely. Okay, what is the computation? Okay, maybe even before I start the lemma. Okay, for just some notation. For a given partition, xs be the following process. Just a definition. Just a definition. Is a continuous, at least local martingale. If M is bounded, then this is a proper martingale. So for a while we will work with bounded guys, and if everything is uniformly bounded, then okay, all the local martingales are martingales. Is it clear why this is a martingale? So just think what you are doing. So on the first segment between 0 and T1, okay, you are doing nothing because this is 0. But imagine it's not, and you start with some concrete value. Then, okay, this is constant, so this is ms. Okay, this is a martingale. Then you arrive at this time, you have some value, which is m0, mt1 minus m0, and then it never changes. I mean, the first term of this sum never changes. All others are zeros before, so this means. And then the second term starts increasing in the same manner. So what you add now is m1, here is again some constant minus m1, and here is ms. It's very simple computation. Okay, this is the notation. Well, if I need anything else, no, I don't think so. So, okay, here is lemma. This is a local martingale which is bounded by some constant k. It is a constant which does not depend on anything. For any need some other notation. Let it be insignificant for a while. And this is a local martingale, which is continuous trajectories. Since it's bounded, I can draw local. It is not our problem now. And the following holds. Actually, what I some convergence in A2. Do we understand what this n means? This n means that now I have a sequence of partitions. So here everything depends on n. Here, again, there are many n's written. Here also would have. Okay. So I have a sequence of partitions. Which are going to be nested. Then for each of them I define this martingale. Then I compute this quantity. And what I claim is that it tends to 0 in V2 for any sequence of nested partitions. Slash somehow, if you believe this is true, then you have a very suggestive way to define first, again, you have a sequence of martingales. You have some estimate of the second moment, so you have Dup's inequality. If you know that, that the expectation at the end, at time t capital squared converges to 0, then you know that they uniformly converge. And so in particular, you can extract, you can pass to the limit here. So you can find a limit of these processes when n tends to infinity, right? So you somehow see a way to construct a local martingale from your process, and okay, it's going to be clear that that's what we need. So somehow this is the very heart of the whole story. I mean, if you believe this is a Cauchy sequence in A2, after that you will see more or less still some page of notational agreements, etc. But you know, it's more. Okay, is it clear at least what I stated? The type of this. Okay, good. And let's try to prove it. It's not that hard. Just compute, this is the goal. Local goal. To compute this expectation for n less than n. What I'm going to do is just, just to use that definition. So, what I need is the expectation of a sum over J1Pn, sum, now I need two indices. Pn and J minus 1n and Ci minus 1n and two increments. And Cj minus n, Cj minus 1n, and another increment. Again, I'm going to say that basically many of them are zeros, provided we had, this segment, tj minus 1 tj, does not intersect that segment. Okay? Then by Martingale property, this is 0. Okay, what is non-zero? What should I do? I claim that the only non-zero case And partitions are nested. What it means that this longer segment should contain this small one. Okay, so let me write it this way. MT, sorry for the annotation, I was unable to invent anything better. So what is J of I? The picture somewhere here. So I have one partition which is relatively coarse in red, and the final one in yellow. Okay, so if this is J, this is lost. This is my I of J. The way around. This is J of I. Gosh, and I don't have all the chalk anymore. This is I. Okay. And again, two increments. Now what I do, here I have a yellow increment, so this is yellow increment, and this is red increment. No. Okay. I'm almost lost already in the very beginning. So, yet again, yes, the other way around. Let me just rewrite it here. This is J of I, this is J of I minus 1, and this is just I. Pardon?
I minus 1. So
I minus, yeah, oh yeah, I minus 1. So this is red, this is J. This is red, and this is yellow. Okay, now what I would like to do, I would like to say, okay, here I have an increment over a long interval. So let me split it into a sum of the corresponding yellow increments. And again, what I would like to say is that many things cancel out.
Sorry, could you say again what is
J of I, so the yellow partition is the subdivision of the red partition. So the only increments that do not vanish in the expectation are of this kind, when the red interval just covers the yellow part. Then J of I is this context. Okay. So now what I'm saying is, all right, I can rewrite it the following way. This is the expectation of a sum of, again, m the same J I minus 1 T J minus 1 n and T I minus 1 n. And now the only non-canceling guy is the square. Is the square of this. Just because, imagine that we rewrote this as a sum of many yellows. Then again, everything except the square cancels. Because all these two, well, they're to the left. Okay, so it cancels, and we have this problem for this problem. And remember, what we computed was this expectation. Okay, similarly, or in particular, I can apply it when m and n are the same. In this case, what I know is that sum over Pm and it should be sum over up to Pm, right? Pm squared is the expectation of xdm squared. This is just a particular case. Okay, there is no j of I minus 1 at all. Okay, good. And now what I need is also the expectation of xn squared. And, well, this. I can write exactly the same formula. And then do my favorite trick of saying, okay, now I have the increment of my martingale over the huge interval, so let me split this interval into many. Non-canceling terms. And now okay, here this is m c j I minus 1 and squared, and here are the increments. Hopefully we're almost done at this point. So what happened is that here I had a summation over j's, but then I rewrite this increment of the martingale as a sum of small increments and not in squares. So, okay. Now we can just compute what is the expectation of the square. Is m, what do we get? Here, this is a square of the difference mi and mji. So t j minus 1 m minus minus 1. Other way around. Here m squared by this squared. NCI minus NCI. So this is the formula. Okay. If you didn't follow, this is just a straightforward computation, and the only trick which is used is that any time when you have a square of the increment of your martingale multiplied by something depending on the past, then you can open the brackets and replace the square of the increment by the sum of the squares. That's an expectation. Okay, and then what? Okay. Let's use some stupid inequalities. So first, you say this is the sum of products. The first I estimate by the maximum, and the rest I keep. So this is PM2 of this. Of this squared by the sum of what I have. And then use Cauchy-Schwarz to say it's less than expectation of this maximum. To 4, 1/2 by the expectation of this sum squared 1/2 at the very end. It's not visible, but it's there. Okay, so we are pretty close to the end. So what do we know? First, we know that trajectories are continuous. Because of that, we know that this tends to 0 almost surely. And we are in the bounded setup. So because M is bounded, everything is uniformly bounded by 2k to the power of 4. So almost sure convergence implies that the whole expectation tends to 0, since we are bounded. So the only remaining part is now to check is that, so question, to bound the second factor. Why bound? If we are able to prove that the last factor is bounded, we're done. So, yet again, what happened? It was a computation. Then here is the result. Then we use, okay, we split the terms. For the first one, we use the continuity of trajectories. And for the second one, it's going to be some additional computation, like another 5 minutes to check that it is also bound. Okay, let me continue right here. Wanted. Just let me rewrite it. The expectation of this sum squared is uniformly bounded. Okay, again straightforward. Just open all the brackets. Sorry for this. So first, it was first there are terms of colors form, and second there are P less than Pm, and I'm going to drop M here in the notation, so because we need to check the bounds, so okay. No need to keep track of that. Expectation. This one, expectation of the product. Okay, then do just the idea is the following. So we know what to do if this is the expectation of squares. If this was an expectation of a sum of squares, then we are done, because we know that the expectation of the sum of squares is just the expectation of m capital T squared. This is again our trick. So let us reduce everything to this. Okay. First we say for the first term, we definitely know this is less than there are 2k squared by the square. This is a stupid estimate, but at the end of the day we have some problem. So for the second, imagine that we fixed first I and then sum over all k's. So what we have here, I mean, when summing over all k's, okay, this is fixed I, use the fact that the expectation of mtk minus mtk minus 1 squared is the expectation of the same blah blah blah, the mt squared minus m t I squared. Just because this is a martingale, this is measurable with respect to FTI, and this is again the trick. And then use that this is less than 50 squared. Well, hopefully at the end of the day, well, not hopefully, it's even written on the blackboard. So what we have here is some constant, which I'm not sure I can keep track of, some constant like b squared by some the expectations of NCCR minus Deterministic constant. And again, we know this is the expectation of mt squared. We are done. Okay, not pleasant. Nevertheless, it works. So, yet again, the only information we use is, this trick with the squares. Nothing else. But eventually what we have, as the result of all this is the following. So this is the bottom line of what we have now. Okay, now given, say, bounded martingale with continuous trajectories, I can and the sequence of nested partitions. I can construct martingales of this form. And I know from nothing, I just derived it in my lemma, that they form a Cauchy sequence. Question? No? It's okay? Well, we can discuss in the break. Well, it's kind of an answer of this. So, I have a Cauchy sequence. Then, okay, I have my tool, my Dooms maximal inequality. So, what I know is the Cauchy sequence is a sequence of continuous functions on 0 t capital, and then I can subtract the subsequence. So, in fact, I already have in my hands some martingale, which is, which actually makes the job. So, okay, that's what we have. Actually, this limit is exactly what is denoted in the theorem by m squared minus the quadratic operation. So remember that I needed to construct some local martingales related to m squared. And this is why, okay, I find this computation important, because on the one hand, nothing happens. On the other, this is, this is exactly the cornerstone of the theorem, how to construct this process. Okay, let us make 10 minutes break, and then hopefully prove this theorem.